Hi, welcome to another video. If you're new, my name is Dave Thomas, also known as 7sharp9. Today is going to be another episode in the monogame F# series. This time we're going to be taking what we did last time and seeing what it would look like in an Elm architecture style. This is an exercise I did after last week's video, or the week before. The last video anyway. This is an exercise I did after the last video just to see what it would look like. It's slightly different to the normal Elmish architecture because the update does not always drive a view update. So the view and update are completely decoupled, and this is because in monogame, if a view is being rendered or certain settings are turned on, there might not be a view for that particular update. So if everything's rendering really slowly, a view or draw operation will be suppressed. So I've coupled this exactly the same in the Elm architecture version that I'll quickly show in this one. There was talk on social media about how functional games might look. So I did this as an exercise just to turn it into a more functional orientated way of doing things. Although the draw and update function and load and init in monogame are quite friendly to do, it just requires a bit of mutation at the beginning. So in this new architecture that I'll show first, it kind of makes it a little bit better, but I'm not completely happy with it. To be honest, it's probably simpler to just use the architecture that's in monogame itself. And after we've been briefly through that, I'd like to continue and we'll add some animation to our sprite. So when we move it about on the screen, you will see animation frames update. And it will be like our little skeletons walking across the screen. So I hope you enjoy the rest of the video. After the last video, I decided to make a quick version of the last video, but using the Elm architecture. So what I did is I took the typical Elm architecture from Elmish and I basically copied the code and adapted it for use with monogame. These parts dispatch sub commands and the command module are pretty much the same as in the Elmish repo. Where things start to differ are in the program dispatch, and I also have an Elmish game which is acting as a base class for monogame. We inherit from game, we have a couple of optional default properties, height, width, and we set these to a standard size, 1280 by 720, and we set up the graphics device manager with the back buffer width and height. Then we also add 3 events, draw, update and init, and these are to tie into the monogame methods that you override in your derived class. So we've got our 3 events, draw, update and init, and we've got these publicly available. We use the CLI event, so they become CLI compliant events, and we use the publish property on the event we defined here to publish the event outwards. And then in our draw, update and initialize, we trigger the event on draw, trigger the event on update, and we trigger the event on init. We don't bother with load content. Load content is called directly after initialize as the last call. So what I would like to do is use initialize as an area in here anyway where we can load the content from models and sprites, etc. The place where things start to really differ is the program runner. We take an Elmish game as our app, and everything else is pretty much the same apart from in process message we have a standard dispatch loop where we call the update function that is passed in when we actually create an Elmish type program, but we update the model and we also call any new commands via dispatch, but we don't update the view. And this is because in monogame, view and update are decoupled, so every update that occurs in monogame, you may or may not get one view called per update. If view is not called, it's for reasons like there was not enough time and we're skipping frames, or a fixed time step is set up as part of the game implementation. So if you do a fixed time step and then update takes too long, then a certain amount of draw calls will be omitted to try and catch up. So our process message doesn't call view, it just calls update. Our update view is the same, it calls program view and that's it. So update view is driven entirely via the subscription to the event. You can see here that our Elmish game that's passed in, we subscribe the draw event into the update view. So every time draw is called within monogame, our view is updated in our Elmish game. This fits the monogame model a lot better than a blind view update following every single update. We don't want to be blindly updating draw when specifically monogame is suppressing the draw call. So they're the main differences. I'll leave a link to the repo so you can have a look. You can also see that the init event is used, so whenever init is called, start loop's called, and start loop is the beginning of the main program loop run. So in here we get program init is called, we generate an initial model, we set the dispatch thunk. Reset isn't used yet. I haven't added the aspect of hot reloading. I'll do that when I get a bit of time, because I want to make progress on actually doing these demos of specific parts of monogame before we start to get into the tooling around games and things that would really help, like hot reloading. So it's a little bit more advanced. I haven't wrote the code for it, so we'll get to that in a future episode. Subscriptions are pretty much the same, and change program, reset view, set current model, and program are all pretty much the same. Trace update is the same, so that's all pretty much identical. So in here I've actually created a module called app. We've got the same old sprite class, sprite type that we had before, and we've got our model which has a player, game time, game, and a sprite badge. We've got a message, we've got a tick, and a move player message. So the tick message is going to be generated whenever there's an update, and we've got an initialize player function which sets up the loading of the skeleton that we saw last time and sets up the various fields on the record. Init model, which is just a helper to initialize the model. Again, we've just got init game, which calls init model, passing in the game time to get our initial model. We've got the key down, get movement vector. They're all exactly the same as last time. The place where things start to get a bit different is we have an update function, and in update we match the message on tick and move player, and if tick is occurring then we generate the new next command. So if we detect that motion has occurred from the keyboard state, we create a new command called move player, and we change that into a command by calling command of message, and we get back a model with the game time updated and the next command, which is either move player or command none if there was no movement in that particular update. If you can imagine, on every tick, which is driven by the update function, which I'll get to in one second, every time there's a tick, there may or might not be a movement. If there is a movement, we generate a move player command. The move player command will then be called here via the extra commands which are processed on every message. So if the player is moving, then we create a new position, and this is code all from last time, and we just updating the model with the new player's position, but it's based on the state going through this game loop. And in view, because views are created from scratch on every frame in monogame, we simply clear the screen as usual. We begin a sprite batch which was contained in our model, and then we do the draw call and we end the sprite batch. The piece where this is slightly different from other implementations is, although this looks very much similar to Elm games. Elm games have a subscription where they tie into normally the animation ticks from within the browser infrastructure. So we basically do the same here. We've got a program with subscription and we do map event subscription, which is here. And all of this does is this ties into the update event that we added in our Elmish game, and we map that into a message called tick. So whenever there's an update, we create a message called tick, which then gets dispatched back into our infrastructure. And it kind of looks okay, but again, like I said earlier, it's probably simpler just to keep to the standard mono game architecture. What I'd like to do is keep this very simple, more like a library than a framework. If you want something more prescribed, which is kind of like a complete framework with commands, there's a library called, I forget what it's called, Elmish? So I'll leave a link in the description anyway. The one that I'm trying to do is kind of more like a library where you can assemble individual components, which fits directly into the monogame architecture where the view and update are completely decoupled. So now that we've got the that slight digression into Elmifying a monogame application, let's get back into adding some animation to our sprite. So here we are in the normal project, not the Elmish style, and the first thing we're going to do is create an animation type. This is going to be a normal record type. We're going to have frames per second, current frame, frame timer, frame length, and a size. The next thing we're going to do is create a helper function because we need to create a strip of frames. If we take a look at the skeleton sprite sheet, you can see that the first column contains the idle animations, and to the right it contains the animations for up, left, down and right walking sequences. So what we need to do is create a new module, and we'll create a function within that to give us a strip of horizontal animations. So we use the list comprehension and we loop between I and the frame count -1. Then we use the offset plus a new point with the size of x times by I to give us each of the rectangles in sequence. So now we can go back to the create function that we were writing earlier. We can use the horizontal strip function we've just wrote to actually define the frames in our animation. The other parameters are given default values apart from the frame length, which is the number of seconds divided by the frames per second. We also create another member called current frame, which just gives us easy access to the current frame. Next we're going to create a module called animation. We're going to create a helper function called reset, which resets the animation back to the current frame and also resets the frame timer. We'll also create an update function which updates the current animation frame if a timer has elapsed. So if the frame length is exceeded, then we increment the frame by 1. We use the normal record update syntax to do this. We now create a discriminated union called animation key, which describes the different types of animations: idle left, right, down and up, and walk left, right, down and up. The last type we need is called animated sprite, and it essentially captures the animations in the sequence, the current animation, whether the sprite is animating, a speed and a position. So it's really similar to the sprite that we defined last time, apart from this one can be animated. We also define two members, current animation, which is a shortcut to get the current animation based on the current key, and also the size. We create an animated sprite module here with reset animation, which passes in a key and an animated sprite, and we use this to return a reset animation for that particular key. And we also do the same with update animation using the animation module's update function. We also finally define a draw function in this module. This is slightly different to what we've done last time, as last time we created draw as a member, but this time we're going to use a module function. This is typically how a lot of functions are defined with F#. You use a module rather than a member function, so you can keep all specific functionality for a type inside the module rather than having it inside the actual type itself. So now we're into the game functionality. So we're going to create two mutable variables, new player, which is our animated sprite, and player animations, which is our sequence of player animations. The first thing we're going to do is modify get movement vector so that when a player is pressing left, right, up or down key, the corresponding animation key is returned as well. So now we're in the initialize code. So we want to create a frame size of 64 by 64 and define a sequence of animations for idle and walking. So we use animation create to create a sequence of frames for each of the animation types. So the idle animations, they only have one frame. We set frames per second to 1 because there's only one frame. This is kind of arbitrary. We use the frame size and then we use point as the offset. So these are just offset by exactly 64 for each of the columns downwards on the sprite sheet. The walking animations follow the same pattern except we have 8 frames and we set it to 10 frames a second, but they use a similar offset apart from the offset 64 in the x-axis first. So now we're in load content and we define a brand new animated sprite. We use the same sprite sheet as before. We set our animations, we set the current animation key to idle down, we set a speed and a position. Now we have to modify update to get the code compiling again, because if you remember we modified get movement vector to also return an animation key. So we add a motion vector, an animation key here, and then we clean up this a little bit by checking for 0 first, and then if the motion vector is actually 0, we return the motion vector which is 0, but then we return false for the is moving. Now we need to write a little function to assign an animation key if there's no movement. So if you're moving to the left and you stop, you need an idle animation for the left. So now we add a little function to do that. We call it walk into idle and we just map over the discriminated union. So if it's a walk up, we map to idle up and so on. So now we can continue this function by using the walk into idle function and passing in new player.current animation key. So we correct the variable name and at this point I decided to use the static function, so we didn't actually mutate the motion vector because we don't really need to do that. So we pass the motion vector in and we return true because we are moving, and we return the new animation key which we got from the get movement vector function. We can modify new position so that we can pass in an actual player rather than it work on the player variable. We can work on the one passed in. Correct the size, which we had uppercase in our animated sprite. I'll quickly correct these to a better name. Now the final piece we can do is we'll actually comment out the updating of the player and we will add in a new animation for the animated sprite. The new animation will be different depending on whether the animation key is the same, in which case we will call update animation. If the animation key is different, we will call reset animation, because when an animation resets you want it to restart to frame 0, but if you update you want to update the frame time and frame that's changed since the last update. So now we update our new player using the record update syntax. We set a new position, we set is animating depending on whether the sprite was moving or not. This makes sure that we don't update if the sprite's stationary. We update the current animation key and we also update the animations. The final piece here is to actually just draw our sprite. For this we use the animated sprite module's draw function that we created earlier on. So now let's start debugging and see what happens. So we've got our skeleton on the screen. If we move using our cursor keys, you can see the sprite now animates in the relevant direction that you're moving in, and he returns to the idle position when he's not. As some of you might know, I recently launched a Patreon page to help support me and this channel. And so far it's been a really good success, and I'd like to take this opportunity to thank everyone who's pledged to me so far. I'm hoping to use the funding that I get via Patreon to help me make more of these videos and more often. And also, as I'm a freelance programmer, it's hard to squeeze in time to make videos in between contracts and things like that. So if Patreon ends up becoming successful, hopefully it means I'll have to take less contract jobs to pay the bills and I'll be able to spend more time making videos for you guys to enjoy. So I would just like to say a really big thank you to everybody who's supported me so far. Thank you very much. So if you've made it this far, why not subscribe to the channel and maybe hit the bell notification so you can get notifications when my next video is out. And as usual, smash the like button as hard as I possibly can, and hopefully I will see you next time.